In the last podcast about frequency tables and histograms, we talk about collecting our data, and the first step is to organize that information so that we can describe that data. Using frequency tables and histograms is one method of descriptive statistics. In this podcast, we're going to talk about another method of descriptive statistics. In this case, we're going to describe the data using numbers. So not just a visual representation, but now we're going to describe our data set using very specific numbers. Here is a histogram that we talked about in the last podcast of our frequency tables and histogram podcast. So as you recall, this is a distribution that deviates from normal. The deviation is considered to be a negative skew because the left tail is longer than the right tail. So what's interesting when we start to talk about and describe our data set, the first thing that we do is something that's visual. So do you think this histogram and the data that comprise it is any different on this score of the first statistics quiz than this histogram of another class for scores on the first statistics quiz? Visually, you could say that they are different. So how you would describe that difference, just using our visual representations, is that the second distribution is more normally distributed, it's more symmetrical, whereas that first distribution, as I said before, is skewed negatively. So it is not symmetrical, it's deviating from that normal distribution, such as this one, and it's deviated in the negative skew or the negative direction. What's interesting, though, is that we might not be as positive that they are different. They visually look different, but we really can't be sure if these two distributions are different until we use numbers. So we're going to use a particular characteristic of distribution known as the central tendency. And this is going to be really important when we start talking about differences between groups, that even though visually they may look different, they really might not be different when we get down to comparing those numbers, particularly comparing those measures of central tendencies. Measures of central tendency give us the one best data point to represent a set of scores. So a frequency table and a histogram don't give us that kind of one word that can describe our distribution. And that, I don't really want to say one word, but that one number that in a sense can give us a clear depiction of our data. It gives us an overall representation of the pattern in our data, but central tendencies give us an ability to say with one number how our data sets are similar or different. Another way to say this is that the central tendency refers to the statistic that best represents the center of a data set, the particular value that all the rest of the data seem to be gathering around. It is what we mean when we refer to a typical score. The central tendency is usually at or near the highest point or the peak of a distribution in a histogram. It's not always, but in some cases it will be. For most of statistics this semester, we will be looking at how our data are distributed and comparing it to something else. We could compare it to another sample that we have data for, or we could compare it to the population as a whole. Knowing the center of our data set enables us to begin to make comparisons. It is the typical score or center score of one data in comparison to another. So we can say, are they similar or are they different? So really, we're moving away from, I mean, we always describe our distributions due to the pattern, so we represented it visually, and then we take it one step further to kind of talk about that specific, the specific description of that data set using numbers. So measures of central tendency really allow us to begin to make comparisons between groups. And for most of this semester, that's what we're going to be doing. So there are three different measures of central tendency that we'll be talking about in this podcast, and that is the mean, the median, and the mode. Most of these you've probably come in contact with earlier in your education, so we're going to review them very quickly. So the central tendency we call the mean is so important that we can describe it in 4 different ways. So in words, the mean is the average of a group of scores. We're going to be talking about the median and the mode in this podcast, but for most of the semester, we really tend to focus on the mean. And there's a reason why we will do that, as you will see much later on in the semester. The mean in plain arithmetic is calculated by summing all the scores and dividing it by the total number of scores. You have no doubt calculated the mean many times in your life. What I'm going to go over is how we represent that number, particularly using symbolic notation and the formula. So for statistics, particularly for this class, your symbolic notation and your formulas are very important. Visually, we can think of the mean as the point that perfectly balances 2 sides of a distribution. And finally, we can look at the mean in symbolic notation. So symbolically, the mean is the average of a set of sample values. It's expressed as either M in written journal articles, but for psychological statistics, when we're doing calculation, we don't use M, we use specifically X bar. So that funny symbol, that symbolic notation of the mean when we're doing calculations in class, we will use the X with the bar over it, and it's pronounced X bar. So anything with a bar over it is considered a mean. So know that in a journal article, you might see the mean written as M, but in this statistics class, we will not use M. We will use the traditional symbolic notation for mean when we're doing calculations, which is X bar. Symbolically, we can represent the mean using very specific symbols. So the formula in words to calculate the mean of a distribution, so X bar would be that symbol of the mean of a distribution. The right side of this equation gives us a symbolic representation of what I told you the mean was in words. In terms of that notation, if we look at the numerator, we have a symbol, sigma, capital sigma, that is the Greek symbol for sum of. So we're going to sum all the scores. So in this case, X represents a score, an individual score, and that sigma implies that we are summing all of the individual scores. So the numerator, this is your symbolic representation of what you know the mean to be in words. That is the sum of all observations, the sum of all scores. And then the denominator is n, and that is the number of scores that you have. So you know what the mean is in words, and here it is represented, particularly for statistics, in symbolic notation. What's really important to note about the mean is that it's very sensitive to every value, and that's because you're using every value in order to calculate that mean. So one extreme value or one outlier can affect the mean dramatically. So just to go over, our X bar is our symbolic notation for the word mean, which we will use in this class. And it is equal to, in words, the sum of all of our scores of all of our observations divided by the number of scores that we have in our distribution. In symbolic notation, that is represented as sigma x over n. Here are a set of single scores. Participants rated their confidence level in passing statistics. A lower number is less confidence, a higher number is more confidence. The scale was based on a scale of 1 to 10, again, where 1 is low confidence and 10 is high confidence. So let's find the typical or the mean confidence rating in this set of scores, this distribution of scores. So step 1, you're going to add the scores, sigma x. So you should get 87. Then you're going to count the number of scores in your data set. In this case, we have 20. You're going to divide the results in step 1 by the results in step 2. Again, rounding to 2 decimal places because we have just done a calculation. Our mean is now 4.35. So you would represent this as x bar equal to 4.35. So now let's talk about another measure of central tendency known as the median. The median, in words, can be described as the middle of a set of scores. So this is the point at which one half of the scores fall above and the other half fall below. It's considered to be the middle score of a set of scores when the scores are arranged from highest to lowest. We don't have a symbolic notation for median, so when you write any calculation, you're going to use the word median to denote the score that is the middle score. So we can describe the median using arithmetic. And in this case, you're going to line up all the scores from lowest to highest. From highest to lowest. From highest to lowest. And we mean all the scores. So if you have more than one score of the same value, they should be lined up next to each other. So again, to reiterate, the median is the middle score. After you line up all the scores from highest to lowest, you're going to find that middle number. Here's a very simple example for incomes from 5 different households. And you're going to line them up from highest to lowest and find the middle score. So here I've done that for you. Step 2, find the middle score. That would be $37,668, and that is the median. Sometimes we have data sets where there's not an exact middle in our data set, and that's because we don't have an odd number. So we'll talk about how to do that in the next slide. What happens when we don't have an exact middle score? So what happens when we have a distribution that doesn't have an odd number of observations or an odd number of scores? Because when you have an odd number of scores, you can take that exact middle and then half of them will be above and half of them will be below that middle number. So when we have an even number of values, we don't have that exact middle. So what we need to do is we need to take those two middle numbers. So no exact middle, it's shared by two numbers. So if we take this original data set of 6.72, 3.46, 3.60, and 6.44, we're going to line them up from highest to lowest. And then our two middle scores, because we don't have an exact number of scores, we're going to take those two middle ones, that 6.44 and that 3.66, and what we do is we add them together, divide by 2, and we're going to come up with now a new calculated median. So this median and this point, at this point, the median for this distribution is 5.02. So what I want you to do is to take this data set, and I want you to try to calculate the median of this data set. If you need to, stop this podcast. Actually, not if you need to, you really should be stopping this podcast, writing these numbers down, and trying to calculate the median on your own. If you're confused, don't worry about it, because we're going to do this in class during the next class where we cover central tendencies. If you've lined up all of your observations from highest to lowest, you're going to notice that there is no exact middle because it's an even number of observations. So you need to find the average of the two middle. And in this case, your median, because you're doing a calculation, should be rounded to 2 decimal places. In this case, it's 4.00. So the easiest of central tendencies is the mode. The easiest meaning it's the easiest to calculate. So in a sense, we've saved the best for last. And in words, the mode is the score that occurs most often. So if you notice, all of these measures of central tendency are talking about a distribution in one particular number to describe the center of that distribution. And we can describe the center in terms of the mean, we can describe the distribution in terms of the median, and we can also describe the distribution in terms of the mode. And distributions might have vastly different mean, median, and mode depending on how those scores are distributed. So the mode, the way we find it using arithmetic, is you list all the scores from highest to lowest, just like you did with the median. And then what you're going to do is you're going to count the number of times each value occurs. The value that occurs most often is the mode. The mode doesn't have a symbol associated with it. So in this case, you would just use mode is equal to, and then write the number after that. So there's no symbolic notation to represent mode. Note that the mode is the score that occurs most often, not the frequency of that score. You can easily determine the mode by looking at a frequency table or a histogram. It's not as easy to determine the mean or the median, but it's very easy to determine the mode because, again, the definition of the mode is the score that occurs most often. So in this distribution of scores on the first statistics exam, you're going to look at your different scores on the x-axis and you're going to determine which score has the highest frequency. So in this case, 10 is the mode for this distribution. 10 is the score that occurred most frequently. If you said 12, you may have done what a lot of people do when they first calculate the mode. 12 is the number of times that the score of 10 appeared in the distribution, but we don't want the frequency, we want the score. So the score of 10 is the mode. So here is our score of 10. The height of that bar is the highest with the frequency of 12, and so the mode for this distribution is 10. So here are a set of numbers. And again, here are the numbers for students who rate their confidence in passing statistics. You're going to take this distribution and you're going to reorder it from highest to lowest. And you're going to notice that the score that occurs most often is 3. So 3 is your mode for this distribution. If you got 27, again, you're reporting the frequency instead of the score. When it comes to mode and for distributions, we can describe different distributions using different terms. So if a distribution of scores has one mode, like in this example, it's called a unimodal distribution. So here is a unimodal distribution of scores on first statistics quiz. It has one mode, therefore it's unimodal. In the previous example, we also got one mode. That mode was of 3. And in that case, it is also a unimodal distribution. Once we actually determine the modes, we can now describe these two different distributions using that number, and we can see that they are different. We can describe them as different distributions. Whether they're statistically different, we don't really know that, but we can say that using descriptive statistic, the last distribution had a mode of 3, this distribution had a mode of 6. So students behaved differently, performed differently on that first statistics quiz, where one distribution they scored a little bit lower, the other one they scored, at least according to the mode, they scored higher. If every value in a distribution contains the same number of occurrences, then there isn't really a mode. So in this case, we would call it a multimodal. There are just too many modes. So multimodal is for anything that has 2 or more modes. We can describe this distribution also as a flat distribution or a square distribution. The more accurate term, particularly in statistics, it's a square distribution because that's what it looks like. We have specific types of multimodal distributions. So in this case, for hair color, we can look at the number of people in a distribution who report themselves as having red hair, blonde hair, brown hair, or black hair. And in this case, you can see that there's 2 hair colors where the frequencies are exactly the same. So in this case, brown and black have equal frequencies of 45 in our data set. So this would be generally a multimodal distribution because there's more than one mode, but more specifically, we call it a bimodal distribution because it has two modes. Now that you've learned about the three different measures of central tendency, we're going to talk about which measure is best. So you might be wondering which measure of central tendency you should be using. Overall, particularly in statistics, the mean is the more precise measure than the median, and the median is more precise than the mode. This means that the most frequently used measure of central tendency is the mean. However, the different measures of central tendency can lead to different conclusions, so there are times when it is better to use one measure over the other. So rather than asking which measure is best, it is better to ask when we use each measure. In general, which measures of central tendency we use depends on the type of data we want to describe. The mode is typically used in three situations. First, when one score dominates a distribution, we can easily use the mode. If the distribution of data is bimodal or multimodal, the mode would also tend to be the most appropriate choice. And finally, we use the mode when the data are categorized as a nominal variable. So let's take a look at an example. Here's a table that displays the political party affiliation of 300 people. So this is a frequency table for party affiliation. If we use the mean, what would we really be able to conclude? That everyone is close to half Democrat? That doesn't really make sense. So again, which measure of central tendency we use is the one that makes the most sense and is most representative of the data. So in this case, the most appropriate measure to use is the mode. The mode being the value that occurs most frequently. So in this example, almost half, or 140 people out of 300, are considered to be independent, or they self-report as being independent. Although the mean is the most frequently used measure of central tendency, there are times when the mean is not the most appropriate measure to use. For example, we saw that the mean did not lead to any meaningful conclusions when we were trying to describe political party affiliation or nominal data. Another occasion when using the mean is not the best choice is when the distribution of our data is skewed. The distribution can be skewed in general, or it can be skewed because there are extreme scores or outliers present. In either of these cases, the median is our best measure of choice. Here is an example of how using the mean and the median can lead to different conclusions and why we want to think about which measure to use. So a New York Times article published in 2005 reported on a record high housing price in Manhattan, record high housing prices in Manhattan. The reporter said the mean price of a home was over $1 million. However, on closer inspection, the median price of a home was really $750,000. Remember that outliers do not affect the median. So the mean housing price was inflated by a few outlier homes that sold for millions of dollars, such as the $7 million apartment sold by Gwyneth Paltrow. So we want to use the median when we have a skewed distribution, or we have a distribution with outliers. Here's another rather funny example of when we should use the mean, the median, and the mode. So finding out what the average salary of a company is, you can get three very different pictures of your data set. So in the first case, it's a mean value of 90,000, a median value of 80,000. But when you start to find out the mode, most of the people working at that company actually make a lot less than 90 and 80,000. Let's look more in depth at the idea of the mean as a balance point. If all of our frequencies are distributed symmetrically, we would be able to balance all of the mean in the middle at the highest point. We could also figure out that the median and the mode are the same as the mean. So with normal distributions, we would find that the mean, the median, and the mode are the exact same score. So with this normal distribution, we find a median, a mean of 5, a median of 5, and a mode of 5. In the case when the distribution is skewed, we're not going to find the same pattern. In this skewed distribution, we find that the right tail is longer than the left tail. And so in this case, we would call it what type of skewed distribution? If you said it's positively skewed, you are absolutely correct. So the tail of the distribution is pointing to the positive or the right side. So in the case of a skewed distribution, for a positively skewed distribution, our balance point is going to be moved towards that positive direction. The skewed distribution places an imbalance in the frequencies, so we need to balance it, just like a seesaw. So in this type of distribution, we're going to find that the mean is 6, but now let's figure out the median and the mode and see if it's the same as the mean. So the median is defined as the middle score, and with 51 scores, the middle score works out to be 5. The mode being the most frequent score, and in this case, the score with the most frequency in the distribution is also 5. So as you can see, the mean is much more sensitive to a skewed distribution than the median and the mode. Therefore, the mean is not always an accurate way to describe a distribution. Now, if the distribution is skewed negatively, we need to again adjust our balance point, or our mean, in order to bring it back into balance. So here the mean is towards the lower end, so it's going to be affected by the lower scores in the distribution, that tail. The mean is calculated to be 4.7, but when we look at the median, it's still 5, and the mode is still 5. So again, the mean is much more sensitive to the shape of our distribution. So in this case, when our distributions are skewed, we are more apt to not use the mean because it's not a good representation of our data. It tells a different story. The mean is also affected by extreme scores much more than the median or mode. So in this case, where we have a huge outlier, you notice that the mean is 7 and the median and the mode are still 5. When your data has an extreme score or an outlier, some people report both the mean and the median in order to accurately express the data. In the same vein, we can talk about distributions and central tendency according to the range of values. So in this case, we have a range of values that could indicate a mean of 50.5 and a median of 50. So you might think that with a mean of 50.5 and a median of 50, the data set will probably look something like this. Unfortunately, the mean and the median don't really tell the whole story, so the range can give you more information. So each time we're adding on some additional descriptive statistic, we're allowing people to see more specifically how our data set is represented. So in this case, our mean of 50.5 and our median of 50, the actual data could be something more like this. So we describe the range as the difference between the highest and lowest scores. So for the first data set, even though it had a mean of 50.5 and a median of 50, the range is a lot lower. So we would use the range of 61.5 minus 35 to get a range of 26.5. And that's actually very different than the second data set, which had the same mean and the same median, but in this case, the range was very different. So we would say that the second data set has more variability in its data. So it has data points that are very different from each other. The first data set, those data points seem to be all around each other. So there seems to be less variability. In the second half of this podcast, we're going to talk about variability. So in the first example, this small range, whereas the second example has a huge range. So sometimes the mean and even the median is not the best example, and knowing what the range is can provide important clues to our distribution and a more accurate picture. Now that we've learned about measures of central tendency and which measure we typically use, we're going to talk about variability. So we've talked about finding the central tendency of a distribution of scores. So now we're going to talk about how different scores are from each other. So we're going to talk about the variability within a distribution of scores. And variability is going to become very important when we start talking about finding differences between groups, which is ultimately what statistics really tries to do. Measures of central tendency are important, but it can only tell half the story about a distribution. For instance, most of you would be hesitant to navigate a swiftly flowing river, complete with rapids, knowing only that the stream had an average depth of 5 feet. Maybe another important question we should be asking is how much does the depth vary along the course of the stream? How the depth along the entire path of the stream may help us determine if we are willing to risk our life. So knowing that maybe the variability is large, that might be more risky to you than if the depth is more narrow. The variability of the depth is more narrow across the entire length of the rapids. This question in statistics becomes really important when we start to compare different distributions, and that's ultimately what we're going to do when we do statistical tests. Maybe in the example of the river rapids, the start of the river is really deep and has the most rapids, gradually decreasing in depth until you get to the gentle flowing end where it doesn't matter how deep the river is. Or maybe the entire river is only 5 feet deep, making this adventure incredibly life-threatening. To illustrate, all three of the distributions in this slide have the same mean, a mean of 10. But you can see that there is a vast difference between the individual scores in the three different distributions. The first distribution on the left has no difference between the individual scores. All of the scores are the same value of 10. The middle distribution introduces a little bit more variability. What I mean is that some of the scores begin to deviate or are different from 10, but it doesn't change the mean. The final graph shows the most variability. As you can see, there is only one score at the mean value of 10, and some values one value away, either an 11 or a 9, or two values away from the mean, either an 8 or a 12. In this third graph, the mean again is 10, but the individual scores that make up that mean now show more variability. This example should drive home the point that although the central tendency can tell us something about the distribution, this measure fails at being able to compare any differences between distributions. The best measure for this is the measure of variability. Remember that the measure of central tendency, particularly the mean, is a representative score of a distribution. The mean can be thought of as a position. So for these three distributions, the singular measure of the mean, in this case 10, can be used to anchor all the scores in each distribution. It is the score that best describes where the scores seem to congregate or where their central tendency lies. This is easy to see in the left and middle distribution, but becomes increasingly difficult with the right distribution. Variability, on the other hand, can be thought of as a distance measure, measuring the distance on the left and the right of the mean. Some scores have a distance of plus or minus 1 away from the mean, as in the middle distribution, and other scores can be a distance of 2 away, as on the right. As you have probably guessed, a measure of variability is a measure of how different each score is from the mean. So if we know the average of some set of numbers, such as an average height of a group of people, knowing how each of the scores compares to that mean can tell a lot about our distribution. Remember that the measure of central tendency, particularly the mean, is a representative score of the distribution. A measure of variability is also a representative score, but it explains how much these scores are dispersed around that mean. In other words, out of all possible heights that one could be, how are the heights of one particular group of people distributed? Were there lots of people close to the mean height of 6 feet, or were there lots of scores at the short and tall end with a few people having a height close to the mean? How much one score in a distribution deviates from the representative score of that distribution can be defined 3 different ways. The 3 measures of variability that will be used to compare the scores in a distribution, as well as scores in other distributions, will be the sum of squares, the variance, and the standard deviation. As you will see, all 3 measures are very closely related to each other. The sums of squares is defined as the sum of the squared deviations, or the sum of the squared difference scores of each score from the mean of the distribution. The variance is defined as the average of the squared deviations of each score from the mean of the distribution. All 3 of these measures have their own special place in statistics. The variance will come into play later on in another statistical test and is also the means to determining the standard deviation. How close are all of these? Each 3 of these measures of variability contain the same, in a sense, root function, and that is the sum of the squares, or the sum of the squared deviations. Variance is considered an average of those squared deviations, and then the standard deviation is defined as the square root of the variance. So these 3 measures, sums of squares, variance, and standard deviation, allow us to be able to go back and forth between those 3 measures. So if you have the standard deviation and you know how large your sample size is, you can go to the variance and then backwards to the sum of squares. Same thing with if you have the variance and you know the size of your sample, you can calculate your sum of squares by going backwards, and you can also calculate the standard deviation by going forwards. In order to understand the variance, the sums of squares, the variance, and the standard deviation, we will describe in detail the method used to acquire all three of these measures of variability using our earlier example. In particular, we will show it using the distribution on the far right, the one with the largest spread or difference between the individual scores. So with a set of raw scores, such as in the two examples here, can you tell me how much they differ from each other? You may have said something like the scores range from 8 to 12 with a mean of 10. So these two sets of numbers have the same mean and the same range. However, you may be able to see intuitively that there is a difference. The bottom row has more scores near the mean compared to the top. However, in stats, we don't like to use words to describe the characteristics of two sets of numbers. We really like to use numbers. Therefore, by computing our three measures of variability, sums of squares, variance, and standard deviation, we can see more clearly how similar or different these two sets of scores are. I realize that with only 7 scores, it may be easy to see how different they are, but with large data sets, it will be increasingly difficult to nearly impossible to visually compare how two sets of numbers are distributed and whether the spread of values is similar or different. And for that, we will typically do an SPSS analysis that will allow us to determine the variabilities. So let's talk about the steps to determining how different scores are from each other. So I'll describe it first in words, and then we'll go about calculating it using numbers and math. The words are merely to help you organize the steps in calculating the three measures of variability. As we go through the calculations, I will explain more in detail. So step 1, we're going to find the number of scores. So that's going to give us our value of n. Step 2 is we're going to find the mean of the scores. And remember, x bar is the symbol for the mean that we use in statistics. Step 3, we're going to calculate the deviation between each score and the mean, also known as a difference score or a deviation score. Step 4, we're going to calculate the squared deviation of each score from the mean. Step 5, we're going to sum the squared deviations. Step 6, we're going to find a mean of the squared deviations. And step 7, we're going to find the standard deviation of each score from the mean. So steps 1 to 4 get us ready to determine ultimately those three measures of variability in step 5, 6, and 7. So in step 1, we're going to count up the total number of scores in the distribution. The raw scores for the distribution we will use containing the following values labeled x in the chart. As you have already learned, x is representative, or the symbolic notation that we use to describe an individual score. So for this process, in order to find the variability of our data set, we're going to use what is known as a grid method. So this box right here with columns and rows is the grid method that we're going to be using throughout the course this term. So you're going to, in your notebook, draw a grid. So you're going to draw 4 columns and you're going to draw 8 rows. The first row is going to be where we label each column. So you're going to label that first column with the symbolic notation of x, which designates the term for score. And then each row underneath, within that column, is going to be all of our individual scores in our data set. So go ahead and list them. You don't have to do it in any particular order. I did it here just for ease, but typically in class you don't really have to do that. It does make it a little bit easier if ultimately you want to go from this data set to making a frequency table. So we've put all of our x scores, or our scores for our distribution, in the proper place in column number 1. And so now we're going to count the number of scores. So the number of scores is 7. So because we're just doing a count of scores, we don't need to do 2 decimal places. Step 2 is to find the mean. So I want you to pause the podcast and do that for yourself. Make sure to use all symbolic notation and the correct formula. So this is a great review for you to be able to, in words, remember, okay, what are the steps that I do to figure out the mean? And that will then help you come up with that formula. So if you were able to talk yourself through this and basically said in words, what I do to find a mean is I sum up all of the scores and then I divide by the number of scores. That will allow you to see that summing up the scores, sigma x, is really the symbolic notation for the words that you used in order to determine the mean. Summing up all the scores, sigma x, and then dividing by the number of scores, which is n. So again, throughout this course, if you can talk yourself through that, most of this symbolic notation that we use is very intuitive to the words that we would use to describe what it is that we're doing. So in this case, because we did a calculation, we need to now report our answer. So our x bar is equal to 10.00. It's a calculation. We need to round it to 2 decimal places. So what we're going to do is now complete that second column. So each row is going to contain our calculated mean. So go ahead and fill in each row in that second column, which we're going to label X bar. And underneath that column heading, each row should contain your calculated mean of 10.00. Now that you've calculated the mean in step 2 and filled in that second column labeled X bar, which is our symbolic notation for the mean of a distribution of scores, step 3 is to determine mathematically how far each score is from the mean. So to do that, we calculate the difference between each score and the mean by subtracting the mean from the value of each score. So this is known as a deviation or a difference score. So the way we symbolically represent a difference score or a deviation score is x minus x bar. And again, that's just a symbolic representation for what I just said in words. It's the mean subtracted from each score. So we've put in the second column our mean. In our first column, we have each score. So visually, what we're going to do and mathematically what we're going to do is we're going to take 12 and from 12 subtract the mean of 10. And now we're going to get a deviation score. So in that third column for step 3, underneath the heading x minus x bar, which is the symbolic notation of our difference score or our deviation score, we're going to do the mathematical calculation of a difference score for each score from the mean. So go ahead and pause the podcast and try to do this for yourself. So here are the answers that you should have gotten. So these deviation scores seem to be a good measure of how much the scores deviate from the mean. But what are they really telling us? How would we try to tell people what the overall difference is? And that's because if you notice, the deviation scores, some are positive and some are negative. What we would really want to do, most likely, is to report the mean of the different scores, but that actually doesn't work. So what I want you to do is try to calculate the mean of the difference or deviation scores and see why it doesn't work. Go ahead and pause the podcast and figure that out. If you've done that, you will realize that the mean of these deviation scores is 0. And in fact, anytime we do a deviation score, the sum of those deviation scores is always going to add up to 0. And what ultimately happens is that we don't get a good representation of how much, on average, each score deviates from the mean. And it's just a mathematical trick that basically each deviation score, because that mean is the balance point of all of the different scores, sum of those deviation scores is always going to add up to 0. So what we need to do is to get rid of those negative signs. You're asking yourself, okay, to get rid of those negative signs, I can just do an absolute value. Turns out that that doesn't really work. We can get an absolute deviation, but ultimately in statistics, that doesn't really help us. So we're going to do another mathematical trick to get rid of those negative signs. What we ultimately do is we take the deviation scores, x minus x bar, and now we're going to square them. So we're going to, in our fourth column, we're going to label it as x minus x bar. We're going to put that all in parentheses, and then we're going to square it. So this column is known as the squared deviations. So in step 4, we're going to calculate the squared deviations, and why we're doing that is to get rid of those negative signs. So again, in every distribution, the sum of the different scores will always be 0, because the mean acts as the balance point, or the position which all scores will congregate around. So the number of scores to the left of the mean have a deviation in the negative direction, and those in the positive direction on the right will always add up to 0. So logically, if this always adds up to 0, that doesn't make sense, because many different distributions will always have a sum of those deviations that equals to 0. And that logically can't be the case, because we know that many distributions do in fact have a standard deviation of how much each score deviates from the mean. So if we're trying to determine how two distributions are different, obviously the mean of the different scores is useless, because whatever that distribution, they're always going to be as if they're equal, because they're both going to be equal to 0. So what we do instead is another little mathematical trick, which will get rid of those negative signs, and that we can ultimately find out what the standard deviation of each score around the mean is, or the standard deviation. So to get rid of those negative signs, we square it. We square each deviation score. This method is a much more accurate measure of that standard deviation. So what you're going to do now is you're going to take each deviation score and you're going to square that, and the answer you're going to put into the fourth column. So notice how for the second, the third, and ultimately the fourth column, because they're all calculations, those numbers that you're going to report in each of those columns now carries that rounding to the 2 decimal places. It might seem silly just because most of them are, or all of them are, zeros. However, in statistics, this is really fundamental, that this is the way we report our numbers when we're doing a calculation. So don't forget to include 2 decimal places for all of your numbers that have been determined through a calculation. So go ahead and pause the podcast right now and go ahead and determine all of those squared deviations, or all of those squared different scores for each score that's contributing to the mean. If you've done that correctly, here are the numbers that you should get. So we've squared our deviation, or different scores, as a mathematical procedure to get rid of the negative signs. Ultimately, if we just do the absolute value of the deviation scores, it turns out that our calculation is not an accurate measure of our standard deviation. So it turns out that just taking the absolute value of that third column underestimates our standard deviation, which in statistics we really don't like to do. We don't like to underestimate. We actually are more comfortable overestimating. So just remember that although probably intuitively and in the past, it would make sense for you in that third column to come up with an absolute value of each number, but know that in statistics and the way we go about calculating standard deviation, this will actually produce an inaccurate measure of how much each score deviates from the mean. And we're all about accuracy in statistics and precision. So let's go to step 5. So we've now figured out all of the squared deviations in that fourth column. We've made sure to report them to the 2 decimal places because it is a calculation. So our grid work, as far as coming up with the numbers that are ultimately going to play into our 3 measures of variability, has been completed. So now what we need to do is in step 5, 6, and 7, determine those 3 different measures of variability. So what we're going to do is we're going to come up with the sum of squares. So if you can remember, the sum of squares is really the sum of the squared deviations. It's abbreviated as SS, capital SS. And the way we go about doing that, again, is summing the squared deviation. So if you say it in words and you know the symbolic notation for what sum is and what the squared deviations are, you most likely could come up with the formula, which is sigma parentheses x minus x bar squared. So that x minus x bar is a deviation scored. That square is the square deviations, and sigma indicates that we're going to sum up all of the square deviations. This measure of variability, the sum of squares, will be very important later on in the course, but again, it allows us to get to ultimately our standard deviation, and you can go back and forth between all 3 measures of variability because you're going to see how they're related. So you can pause the podcast and you can determine the sum of squares on your own. If you did it correctly and you summed it up, you should get a value of 12.00 for the sum of squares. In step 6, we're going to find a mean of the squared deviations. This is also known as the variance. So the variance is really just an average of the squared deviations. There's a trick, however, when we're coming up with the average of the squared deviations. Typically what we use when we're doing a mean is the number in our sample. So instead of using the number of scores as the denominator, we will use a slightly different number. This number will be the number of scores minus 1. So first let's calculate it, and then I'll explain a little later why we use this number. So if we're finding an average of the squared deviations for our variance, it's going to be the sum of the squared deviations, which is sigma x minus x bar squared, over some count. So typically we use n when we're coming up with a mean, but for variance we're going to use n minus 1. So that is a count that's going to allow us to be unbiased. The symbol for variance is s squared. So if we're looking at this formula, s squared is equal to the sum of the squared deviations divided by some count, which is n minus 1. So again, being able to say it in words will allow you to not really have to memorize the formula, because if you remember what that symbolic notation means, you can very easily remember that formula without sheer memorization. Go ahead and pause the podcast and figure out that number. So if you did the calculation correctly, you should come up with a variance of 2.00. Again, it's a calculation, so we need to remember the 2 decimal places. So the variance, s squared, is equal to 2.00. So now that you've calculated that, let me go through and try to explain why we use n minus 1. Might not be clear during this podcast, but as we get on into statistics, it's going to be a lot more clearer. So I told you earlier that I would explain why we measure variance and therefore standard deviation using n minus 1. So the variance and the standard deviation are estimates of variability in population of scores from a sample of scores. So we typically, very rarely, do we have a population of scores. And in statistics, what we're trying to do is we're trying to compare 2 groups. And we have 2 groups that are samples, but they are representative of a larger population. We don't have that population. So what we're trying to do is estimate what the mean of that population is and what that variability of that population is. So if we're trying to make an estimation of what that variability of the population is based on a sample, we tend to be, in statistics, conservative. Being conservative means that we're trying to be unbiased. So by subtracting 1 from n, it forces variance, which is s, and s squared, and standard deviation, which is s, to be, in fact, larger. And we want our variance and our standard deviation to be slightly larger because it means we're being more consistent. Because ultimately, you're going to see that our standard deviation plays a big factor in our statistical test, and it's usually in the denominator. And a smaller s in a denominator will actually inflate a statistic. So we might actually find an effect when in fact we really don't. So we want to make sure that that variance and that standard deviation ultimately is not smaller, that it becomes larger, which means it's more conservative. So again, remember, being conservative means that we would rather overestimate than underestimate the standard deviation of the population. And if you think about this in words, we are basically saying this, that scores, there's larger variability around the mean than if we underestimate, which means that those scores are more like the mean when in fact they may not be. So being conservative means that we're trying to overestimate, not underestimate. We're trying to say that there's more variability than less, because ultimately, when we're comparing 2 groups, we want to see how their variability differs from each other. In terms of our formula, subtracting 1 from n leads to an artificially large estimate of the standard deviation, meaning we're more conservative. So let me give you an example of what I said in the last slide. So the population and the sample come into play when we calculate the variance. We rarely have the population, so we're trying to figure out a variability of the population based on a sample. So as our sample size decreases, the difference between the biased and the unbiased estimates, so our unbiased estimate is n minus 1, and our biased estimate is n. So let's assume that whatever it is in the numerator and whatever formula we're going to be using is 500 for all of these 3 examples, for sample size 10, 100, and 1,000. So if we were to use n in our formula, we would end up with a bias estimate of the standard deviation. So if the value of our numerator, when we're trying to figure out the standard deviation, the x minus x bar is equal to 500, and we divide by n, then we're going to get a biased estimate of the standard deviation of 7.07. If we take an unbiased estimate of the standard deviation for sample size 10, we will get an inflated or larger standard deviation of 7.45. So the difference between the biased and the unbiased estimate is 0.38. Ultimately, you're going to find out that our probability of finding a difference, so when we start talking about probability in our probability podcast, this difference of 0.38 is huge, and it actually might show a massive error in our ability to come up with an inference. So using that 7.07, we might actually find a difference. Using that 7.75, we wouldn't find a difference. And in that case, as statisticians, we're not really comfortable with that huge difference between the biased and the unbiased estimates. We still have something that, according to statistics, we're still not comfortable with. So if our sample size is now 100, our biased estimate of the standard deviation is 2.24. Our unbiased estimate of our standard deviation is 2.25. This difference being 0.01 still could lead to making huge errors in our conclusions or our inferences. And again, statisticians are not very comfortable with this. As our sample size increases up to 1,000, now the difference between the bias and the unbiased becomes a lot smaller. So as you get closer to the population size, not saying that 1,000 is the size of the population, but that's a pretty large number when it comes to some of the statistical tests that we're doing, then using the biased might be okay, but because of tradition and this idea of being conservative, we always use n-1. So it's not as big of a deal as we get larger sample size, but because of the fact that we don't always have sample sizes that are 1,000 scores, we will, from this point on, always use the unbiased or the n-1 for our standard deviation calculation and variance calculation. All right, so now that I went through this explanation of why we use n-1 in the denominator when we're trying to figure out the average of the squared deviations, which is the variance, our last step in step 7 is to come up with that third measure of variability, which is the standard deviation. So we came up in step 5 with sums of squares. Step 6 was determining that second measure of variability, which is the variance, which is the average of the square deviations. And ultimately, in step 7, what you're going to do is reverse the squaring that you did to get rid of those negative signs. So we're going to now calculate the standard deviation from the variance by just taking the square root of the variance. Because we're taking the square root of the variance, and the variance is s squared, that means that the standard deviation symbolic notation is s. The formula for the standard deviation is the same as the variance, which is the sum of x minus x bar squared over n-1, but we're taking the square root to reverse what we did in that fourth column of squaring the squared deviations. So all of that formula for variance is now, we add the square root over that entire variance formula. And when you take the square root of the entire formula of variance, you should come up with a standard deviation S equal to 1.41. So you can pause the podcast and see if you get the same answer. So just to reiterate, here are the 3 formulas for our 3 measures of variability. So we have sums of squares, symbolically notated as sums of SS, and the formula with symbolic notation is sigma x minus x bar squared. The variance, symbolic notation, is s squared. The formula with symbolic notation is the sum of x minus x bar squared over n-1, or divided by n-1. And the standard deviation, symbolic notation S, is that variance formula, sum of x minus x bar squared, and over or divided by n minus 1, that whole formula, the square root is taken. So that's the end of the podcast for central tendency and variability. I know it's a long podcast, but it's no longer than class would actually be. We will do a bunch of activities during the next class so we can really drive home this idea of central tendency and variability.